So good morning and afternoon, everyone, depending on where you are connecting from. Here in Europe, it's afternoon. And a warm welcome to today's Thermal Transport Cafe meeting. It's a pleasure to have so many people connected, and in particular to introduce Dr. Sepideh Khodaparast. Sepideh is a university academic fellow currently at Leeds Institute of Fluid Dynamics, where she is leading the Biomimetic Functional Interfaces Research Group. Prior to join Leeds University, she was a researcher at Imperial College at the Polymers and Microfluidics Group. And before that, she was in the US, in Princeton University, working on a micro-nanoscale interfacial problems in complex fluid at the Complex Fluid Group at Princeton, as I said. Today, at the meeting today, she will tell us more on how to tune surface interaction for the manipulation of complex fluids. For example, how surface modifications and rough surfaces can impact phenomena such as nucleation and bubble dynamics. So I leave the stage to Sepideh. She will share the screen and go through the talk. We are very curious.
Thank you, Chiara. Thank you. Let me just start. Okay. Is this? Do you see my screen? Let me just go back. Do you see my screen?
Yes, very well.
Okay. Thank you, Chiara. And thanks for the invitation to give this talk. So as Chiara said, I work on different problems that typically involve some sort of interfaces. And I picked a few examples across different applications and different problems that all involve some sort of surface interactions. And what I mean at the end of the title, but complex fluids, is fluids that involve some sort of interfaces, which is typically the fluids that we work on. But these interfaces, they're of different forms, and somehow from left to right, you are looking at the sort of chronologically ordered. So I started with fluid-fluid interfaces, mainly gas-liquid interfaces, and then moved to molecular soft interfaces. And obviously all of the interfaces that we have are sort of molecular interfaces, but these, by molecular soft interfaces, what I mean is interfaces that are formed of self-assemblies of, mainly in the context of my research, they're amphiphilic molecules. And then I'm going to talk also a few examples about if we know about these kind of fluid interfaces and we know about phase transitions in soft interfaces, molecular interfaces, can we actually use this to create materials? So our current research is, in the past 4 or 5 years, is mainly focused on solid-liquid interfaces, but I'm not going to talk about the interactions between the solids and liquids, but mainly talk about how we can tune these some of the phase transitions to be able to create material that then can be used for the manipulation of fluids. So I'm going to give 3 examples.
Maybe, sorry to interrupt. Maybe if you want, it might be useful to use the pointer or the laser, yeah. So we might follow you even better.
Okay.
Amazing. Thank you.
Yeah.
Yep.
Okay. So I'm going to go through 3 examples from the 3 different areas of research that we work on. Regarding the fluid-fluid interfaces, when I started my PhD, we were mainly focused on these. And although my research is to a large extent applied, I'm going to use these applications mainly to motivate the talk that I'm giving today, but I'm not going to go to the depth of any of the applications. So when I started my PhD, everything that I was doing was mainly focused on two-phase flows in microscale geometries. And the application originally was in classical microfluidic, not microfluidic, but microscale confined geometries that were related to oil recovery and hydrology. And what we cared about in these kind of quite different applications was that in the battle zone, in the unsaturated areas where you have either air, water going through these microscale pores, or you have oil and another liquid that's used for pushing the oil out. And these areas are filled with two phases of fluid. One is typically less viscous than the other one. And for example, in the hydrology, normally you have this imbibition and evaporation regimes during which water goes down due to gravity, or due to evaporation, there's gas phase change, and then there's gas water vaporization and coming out of the ground surface. And so in the late 1990s and early 2000s, the applications for two-phase flows in microscale geometry sort of were shifted towards these microfluidic applications. And there were all the applications around microfluidic devices, and especially in the context of two-phase flows and multi-phase flows, they were around these droplet generation of droplets, where you have at least two phases of fluid. And you use these droplets, normally in microfluidics, we use these droplets either as a compartment for treatment of the accurate and precise treatment of the fluids that's inside the droplet, or to increase the mass transfer at low Reynolds number in this kind of fluids. But then there are other applications that, at least in the group that I was working in during my PhD, that was around microelectronic cooling. So here you don't have the two-phase flow normally at the start of these micro scale geometries, but you start as a liquid single-phase flow, but evaporation and phase change leads to having multi-phase flows, two-phase flows. So you would enter with a single-phase liquid flow, but get out of the channels with liquid gas flows. And this latent, you use this latent heat transfer for cooling devices, for example, microelectronic cooling applications. So across all of these applications, if I give you a schematic of what I cared about, was scenarios where we have this lower viscous fluid in the format of, here I'm showing it in these yellowish, for example, bubbles, going through a confined geometry, which is filled with a more viscous fluid. You can have heat transfer or not. And as the lower viscous fluid goes into the channel that's filled with this more viscous fluid, it cannot fill the entire channel because of the surface tension, and there's this thin film of liquid that's formed around it. And mathematicians, they love this problem, especially when it's two-dimensional and it's axisymmetric geometries, because the thickness of this liquid film is directly proportional and almost only proportional to the speed of the bubble. And there's also the parameters such as the fluid properties. But if you fix those fluid properties, then you know that what's the thickness of this film that's formed around the bubble, and how it's proportional to the speed of the bubble. So it's quite a simple problem to look at mathematically. And it's been looked at across since the start of the 20th century. From 1918, there's works on scaling this numerical, there's theoretical and experimental work on scaling of how does this fin thickness and the speed of the bubble scales with the flow properties. And just to summarize this slide, I'm not going to go through this like do a literature survey here, but what you need to know here is that the thickness of the film that's formed around those bubbles or droplets, the non-dimensional format of it is proportional only to the capillary number. So that's the only dimensionless number that we have in the problem, and the capillary number is just the viscous term over the interfacial term. And there's this this power 2/3 that governs the entire problem. Okay, so I've worked in different, mainly in axisymmetric, at least, geometries and 2D geometries. I've been working on doing experiments in different scenarios, and it was the intention of these experiments were mainly to validate numerical schemes or to validate the simplified assumptions that people have done to develop theories. But when you start working across different, even at micro scale, smaller scale, when you start working with different applications, you realize that the only capillary number is not the only dimensionless number that's important, especially when you start working with fluids such as refrigerants. Because of the low viscosity, and especially if you run at a higher pumping pressure, your Reynolds number is quite large. So you start having three-dimensional and transient effects. And even at small bond numbers and smaller cavities and smaller pores, although people tend to still neglect the buoyancy, we see that even at very small bond numbers, we still have the effect of the buoyancy. So bubbles are most of the time are not centered in the channel. But beyond that, if you think about the applications that I was talking about at the beginning, you see that most of these applications are actually quite far from being two-dimensional or axisymmetric. Starting from microfluidics and microevaporator for cooling, you see that these channels, the man-made channels, engineered channels, are normally rectangular, and which is a geometry that's quite far from. So these are aspect ratios around 1. And when you move to hydrology or oil recovery applications, these pores, they all have corners. So we thought that to fix this simplification, or to think at least, to start thinking about this simplification if it's valid for other geometries, the first thing that we started working on was channels that have these corners. So they're simple rectangular channels that you get easily in microfluidic devices. And so there's the classic study of the thin film formation in the same exact problem that we saw lots of literature on starting from 1920s, 1930s. There is much less studies when you move to geometries that have these kind of corners. And what happens as soon as you start adding corners is that you have these liquid film corners that are that the liquid is running at a lower pressure. So you have these lower pressure zones that sucks the liquid from the center of the channel towards the corners. And this suction of the liquid, so here is this part is the nose of the channel, and this is the end of the channel. So as you move from the nose to the back of the bubble, the liquid keeps being sucked towards the corners of the channel, which means that you have a thin film in the center of the channel, but then there are these zones that there's depletion in the film thickness. And so this not only creates this in the cross section of the channel, creates this complex shape in the liquid film. But the problem is no longer also as simple and beautiful as the original problem in axisymmetric geometries. Because of this suction, means that as you move from the nose of the bubble to the end of the bubble, to the back of the bubble, for a bubble of certain length, you start losing liquid towards the corners, and this film becomes thinner and thinner. And the question that we had was, at what point this thin liquid is going to be thin enough that you start having dry out regions. So the experiments that we ran was quite simple. You put the microfluidic device under a microscope and you look at these horizontal walls, so either the top or the bottom, depending on the configuration that you have under your microscope. From the original classic problems, we knew that this bubble velocity is going to have an effect. Obviously, channel geometry, we knew that it's going to change the flow configuration. But the questions that we had was, what was the effect of the bubble length, and especially the wall wettability. So you see in the first video on the top, it's a shorter bubble. It goes across the channel. You have to trust me here that there is no dry out. But when you compare it to the video at the bottom, if I can go backward, yeah, you see that there are these zones where the dry out patches are happening, and that's the zone where the film is getting thin enough, and either because of just the thinning of the film or some sort of interaction with the wall that we start having these dry out patches. So what is the contribution of wall wettability? I promise I'm going to talk about surface interaction. So what's the role of the wall of if you're running the experiments in the same exact conditions, what would happen if you have a more wettable or less wettable wall? In the first video, you're looking at this condition that the wall is quite wettable, but the bubble is moving at quite a low capillary number. So the film is quite thin. And eventually, at some point from the nose of the bubble, you start getting these dry out patches. But because the the wall is quite wettable, the speed of this dry out patches, growth of this dry out front is not too fast. So you can track it actually even with your, these are high-speed videos, but at least in the high-speed videos, you can see them moving. But when you go to channels which are less wettable, you see that this growth of this dry out patch is quite spontaneous, and it fills up the entire channel. So you go from scenarios like the one on the top to scenarios which are like the one at the bottom. And what we cared about, or at least what we could sort of measure and make sense of, was the region in front of the bubble that the bubble was staying wet. If you think about engineering solutions, at least, so think about microfluidics, microelectronic coolings, if you typically use these larger long bubbles because they increase the mass transfer, and especially they increase the heat transfer because of the thin film that's formed around the bubble. But the moment you lose this thin film, you start having these hot zones around the bubble, and that's what you want to avoid. So the idea was that if we have a good prediction model for this wetted film at the front of the bubble, maybe we can help some applications at least. And the scenario when you go to oil extraction or hydrology is way more complicated. So this is just what I was saying. So if this is exactly looking at this is a numerical simulation looking at the heat transfer around the bubble in a rectangular channel, and you're looking at the wall, at the horizontal wall. And you see that at certain regions, so this is just the interface, and the zones which are white is where you see where dry out is happening. And you see that the zones where dry out is happening, so this is the corresponding heat transfer coefficient and Nusselt number, I believe. And so the regions where you have these dry out patches, suddenly you have very low heat transfer compared to the rest of the regions where you have the thin film. And if you now, these are the contact angle of the wetting, basically the wetting condition on the channel. So that if you increase the contact angle, so going from more wetting to the less wetting channel, you see that these zones in the same exact condition, these zones are expanded and you have much less, much lower heat transfer. So in these kind of scenarios, it is exactly directly translatable to what I was talking about. If you move to hydrology, these kind of de-wetting scenarios, especially if you think about hydrology and oil extraction, the walls that you have are normally not smooth walls. And they're filled with particles which are can be detached and translated across the channels. And these particles can, depending on which setting you're in, can be the waste from hospitals that can contain pathogenic bacteria, viruses. And every time you have these dry out patches, or these kind of fronts, multi-phase plants, they can translate lots of particles from one zone to the other. And these zones, they can be kilometers apart from one another. So we have worked across that problem. I'm not going to go through that, but how does this liquid front and dry out performs when you have an extra particle on the, so the geometry is even more complex, except besides those corners, we have also particles on the wall, and how it can translate and transfer those particles and take them away from the wall and take them to another zone. But for now, let's just get back to this problem. If you're now convinced that it's important to know the wetting region from the nose of the bubble, let's just look at what the experimental data tells us. So we knew that this length is sort of should be a function of at least the capillary number, which is the viscosity multiplied by the bubble velocity over the interfacial tension between the two phases. So all of these scenarios that I was discussing, there's always air bubble into water, or water mixed with another liquid, that just to tune the surface tension or the viscosity. There is the geometrical feature. So there's H is represent the height of the channel, W is the width of the channel, and theta reference is some sort of contact angle on the wetting, represents some sort of wetting in the channel. So the smaller the theta, the more wetting the channel is, the larger the less wetting. Okay, so let's start with the speed of the bubble. As expected, you increase the speed, or at least at the same, well, yeah, let's go this way. If you increase the speed of the bubble, so this is just the wetted zone from that's just, for at least for the first graph, I explained this. On the Y, you always have some sort of the wetted zone. At this point, it's still dimensional. And then I'm measuring the wetted zone versus the speed of the bubble. And you see that the curves are shifted. They're always, this is a log-log plot, so they're always some sort of a power law, but they're shifted. If I now use the typical capillary dimensionless number, you see that all of the curves collapse onto one single curve. And the capillary number, again, is just the viscous terms over the interfacial term. And I'm changing the capillary, I'm changing the viscosity of the fluid and interfacial tension of the fluids in all of these. So they all collapse into one curve when you have, when you measure which is what you expect from the other classic problem. What about the dimensions of the channel? Because there we had only the diameter of the tube. Now we have a rectangular channel. So if I look at two different heights of the channel, obviously I get again a shift in the length from the nose of the bubble that's wetted. But for different width of the channel, if I can, so if now I non-dimensional the wetted region over the height of the channel, you see that again, all of the data collapses onto one single curve. So we sort of, at this point, established that the y-axis should be the LW, which is the wetted zone over the height of the channel, or 2 times the height, or half of the height of the channel. And the y-axis should be some sort of a capillary number. But I said that the wetting of the channel does have an effect. And in fact, if you change the wetting behavior of the channel wall, you see that, again, the curves of the data is shifted in the log-log plot. So they're all still having more or less the same power law, but they're all shifted. And in dry out patches, the growth of the contact line motion in dry out problems, we know that the speed of the dry out front scales with for small angles of wetting angles, scales with the angle to the power 3. So it means that the speed that we have in the capillary number here needs to be corrected and account for this dry out contact line motion. So we decided to sort of add this correction term to the capillary number and divide the capillary number with the theta, which is some sort of a contact. This is quite an arbitrary number in our setting. I can explain it later, but over this theta to the power 3. And you see that all of the data collapses onto one single curve. And there is this power law capillary, this corrected capillary to the power 1/8. And so we end up with this particular prediction method that is based on the only, again, predictable, the wetted length in front of the bubble is only predictable with the capillary number. And if you account for, so it's basically the drainage of the fluid towards these corners and the van der Waals interactions that causes this drainage. And if we compare our data with the theoretical data in the field, we know that the dry out typically occurs in this region. So you never get to this for the range of capillary numbers that we studied. The dry out is typically happening in these regions and always starts with this minimum fin thickness. Okay, so it's just a thank you to the people who were involved in this research. And I'm going to move to the next problem, that is these molecular soft interfaces. So as I said, these kind of interfaces, they're made of amphiphilic molecules. So you have the head group, which is in red here, and then the tail group, which is in yellowish tail form, and is hydrophobic. So the hydrophilic terms, so this is an aqueous solution. The hydrophilic terms, they turn towards the aqueous solution, and the hydrophobic term gather together, and they create these kind of self-assemblies, a variety of different self-assemblies. But this is what we call a micelle. In the context of the applications that I cared about, we were mainly involved in but mainly cared about cleaning efficiency of these micellar self-assemblies. And so think about detergents, think about soap. The way these work typically is that if you have some sort of what I call soil is normally dirt. If you have some sort of dirt either on the surface or in the fluid that is not water soluble, these self-assemblies, these micelles can help encapsulate it and make it water soluble, and then it can be washed out. So there is all these kind of different self-assemblies that these can form, but I'm going to go through the phase behavior of a typical surfactant. So you have concentration on the x-axis and temperature on the y-axis. As you increase, let's just move in the x-axis first. As you increase the concentration, you go from these monomers of the amphiphils. They start creating these micelles, and then as you increase the concentration, they create some sort of liquid crystals. What is very important is that for cleaning, high cleaning efficiency in most of the soaps and detergents, you want to be in this kind of zones. And so if you look at the back of most of your detergents, either laundry detergents or dishwashing detergent or hand wash soaps, you see that the concentrations that you deal with is quite high, is 15 to 30%, between 5 to 30%. But consider that these are in the main bucket that you buy, and it needs to be diluted. So when you dilute this, and you dilute this significantly, you want to still stay in this kind of phase behavior. There's one problem with this phase, at least both in terms of the formulation and when it comes to in terms of formulation, when it's being produced and when you want to use it, is that when you reduce the temperature, there are different phase kind of phase transition going from this micellar phase to different phases. So if you increase concentration or cool down around this zone, you go to these liquid crystal phases. But what I'm going to talk about is that when you decrease the temperature, you cool down your solution, you're going to go from these isotropic small micelles, these are nanoscale micelles, to these larger scale self-aggregations, which are in crystal forms. So if you cool down your liquid soap in the kitchen, in the fridge, you will start seeing crystallization occurring, and then you will have the precipitation of these crystals at the bottom of the container. And every time you have crystallization, you're consuming the micelles, so you're significantly really reducing the cleaning efficiency. I'm going to focus on one single surfactant, sodium dodecyl sulfate, which appears in the majority of the detergents that you're using probably at home. And something special about this one is that we use it a lot. But if you look at this phase diagram, you see that the temperature at which the micellar phase switches to a crystalline phase and you start losing your micelles is actually quite close to the room temperature. And with the movement towards cleaning and washing, either a laundry or a dishwashing cycle at lower temperature, and especially these materials being produced in areas with different produced and transferred across different temperatures, there is this issue that the majority of these formulation might go through these kind of phase transitions. So there is that application that is quite important. But what I want to talk about is that how do we actually measure this temperature, which is something that is, so I'm going to talk in the context of crystallization, but it's quite similar to what happens during evaporation. So we typically, to be able to measure this temperature, what we do is either we slowly cool down our solution and detect the first temperature at which the crystallization occurs, or we cool down the solution at fixed temperatures, wait there until crystallization happens. Question is, how do we cool down the solution? How fast or slow we cool down the solution? And if we go down in temperature and wait, how long do we wait? Okay. So if you cool down the solution, let's say linearly and very slowly, if you cool down the solution continuously, if you don't do this slowly enough, you might go below this crystallization temperature and never detect the crystallization. Similarly, if you go down the temperature and wait, if you don't wait enough, then you might miss that temperature. So every time someone reports this is the crystallization temperature or this is the evaporation temperature, you should be asking what technique they used and what algorithm, what protocol they used to change the temperature. Okay, so when you think about techniques that we use different types of techniques that have different resolutions in space and time. And so I already mentioned that the cooling history has a significant effect on the final result that you get. But the question that I'm going to ask today and try to answer is, what's the effect of the volume and the interfaces that you use? Because depending on the technique that you use, you're going to be using a different volume of the sample, and the containers, most of the time, you don't have the choice what container you use. It might be that in some scenarios you're using metallic surfaces as a container, or you can use glass, or you can use polymeric materials. So let's just start with an isothermal test, which is the easiest to compare data. For comparison of data. So we cool down the solution below the crystallization temperature, and we wait and measure the time that it takes for the first crystals to form. I'm showing you the result from two different techniques. The first technique is dynamic light scattering, uses laser. Second one is optical microscopy. So the first technique, the one in red, has much higher resolution, detection resolution in nanometer compared to optical microscopy, which is microliter. And it's a much larger volume, which means that if you have homogeneous nucleation of crystals in the bulk, with this larger volume and smaller resolution, you should detect crystals much faster than optical microscopy. But the result is telling you the opposite, which means that, so look at these numbers. You're seeing this is time to the to the observation of the first crystals, and you see that when you're very close, this is final temperature, set temperature, and this is our crystallization temperature. When you're very close to this crystallization temperature, you have to wait around 30 minutes for the first crystals to be observed. But in all cases, you see the crystals in the first scenario much later than what you see in optical microscopy. And the reason behind this is that the surface area, the solid surface area that you have in relative to the volume of the sample, is almost 30 times larger in the optical microscopy sample. So if I don't wait, so if I'm looking at samples like this, if I don't wait 30 minutes, I might miss this crystallization temperature. That it can be the similar thing in evaporation when I'm working with techniques like this. Besides that, the resolution and the waiting time and the volume of the sample you can have, so we concluded already that we don't have homogeneous nucleation, and all of our nucleation is actually happening on the surface. When you have nucleation on the surface, there is the effect of the heterogeneous nucleation. You have the effect of the surface energy and surface roughness. So when you think about the interface between the liquid that you have and the surface, there are at least two different things that you should be looking at: the surface free energy and the roughness. So I'm looking at the image of the droplet under a microscope. The first scenario, the surface is glass. Second scenario, surface has higher energy, but just plasma treated the glass, and you see that in time. So from left to right, you're going to from early time to later times. You see that when I plasma treat the glass, crystals start happening much faster. And I'm just going to go through these a bit faster. But what you can see here is that this again is the induction time. So the time to the observation of the first crystals, you see that it's much longer for surfaces that have lower energy, so less wetting surfaces, compared to surfaces which are way more wetting, such as plasma-treated glass. And if I plot just the water contact angle as in the x-axis, you see that the induction time for the crystallization to occur, it just increases monotonically with this wetting of the substrate. So that was just with the surface energy. What if we add surface roughness to the scenario? And majority of the surfaces that you deal with, unless it's very smooth glass, metallic surfaces, that typically have quite large roughnesses depending on the machining technique that you use. So these are surfaces that are created by casting sandpaper, and sandpaper has this grit number that the larger the grit number, the smaller the surface roughness. If I plot again the time that it takes for the first crystals to be formed versus the grit number of the sandpaper or the rough surface, you see that there's this minimum value in the curve, and it's not monotonic. It is more clear when you start looking at both the surface roughness and the wedge angle. So you see that the surface roughness goes down with the grid number of the sandpaper, but the wedge angle has this non-monotonic curve. So there is this sweet spot where you have quite small wedge angle, so quite deep tight wedges, but also small surface roughness where we have the highest number of chances of nucleation and crystal formation. So if we go to larger scale, all of these conclusions that I was making under a microscope, they actually still hold. So if you increase in a container, in a larger container, if you plasma treat your glass container, you start seeing crystals forming. So compare these cases on the right from top to bottom. So no plasma glass, plasma treated glass for a longer time, and you see that there are more and more crystals forming. Now, if you add to your container a rough surface and tune the surface roughness, you can increase the amount of crystallization that you get. So again, if you're thinking about a container in which you store for storage purposes, the material of the container, the energy, surface energy of the container, it matters, the surface roughness matters. But beyond that, every time you see or you report or you see reports of temperatures at which surface, at which phase transitions are happening, or the induction time to phase transitions, these are always questions that should be asked really. What material did you use? How long did you wait? What was the surface roughness? Okay, let me just check how much time I have. Okay, I'm going to switch to the third problem where we deal with solid-liquid interfaces. We care about solid-liquid interfaces, and especially structured and rough solid-liquid interfaces, because these are storing, I mean, they've started a long time ago, but they're having more and more applications across different applications, across different industries, really, going from energy to transport to textile and biomedical engineering. And these are only the few different applications that we are interested in. But one of the issues, so we know that adding surface texture, it increases energy efficiency of these materials, it reduces drag in many cases, it reduces the fouling on these surfaces. But one of the issues with creating surface roughness, or at least surface structure and nano and microscale surface structure, is that most of these materials that you want to create these structures on are already established in different applications. So for example, in energy, most of the materials that you're dealing with are in the form of tubes that have curved interfaces, internal and external. You're dealing with meters of material. So if you want surface structuring, it needs to be a technique that is scalable. For textile, it's even more complicated because these are multi-scale materials and they need to keep their deformability, and you still need to think about scalability. When you go to biomedical applications, very similar to the other cases, actually, that you still deal with curved surfaces, and especially some of these, although we've been thinking a lot about durability of these surface structuring techniques, you see that the majority of the materials that we want to have, depending on the application, that we want to have surface structures on are actually single-use materials that have very short lifetime, and we should actually, more than durability, besides durability, we should think about sustainability of the material and the method that we use for this kind of surface patterning. And the thought that we had was that, can we actually, instead of thinking it as a surface patterning and manufacturing problem, can we think about it as a coating problem? So think about all of these materials being their original, in the original format, and we just apply an external coating onto this. And we already have all of this information and physics, know about all of the physics of fluid mechanics of coating. Could we actually mix that fluid mechanics of coating and add an extra level of complexity to it, and add thermodynamics phase change to that liquid that we're coating onto the surface to create patterns onto the surface? And in the past few years, we've been working on creating patterns through condensation and crystallization. I'm going to talk about mainly crystallization now. The issue, and so these ones, they're great techniques for creating patterns in films, and they're great techniques for creating micro and nanoscale structures onto the surface. The issue is that they're phase change, thermodynamic phase change processes, and they're stochastic processes. Question that we had can we turn somehow these stochastic processes into something that's more deterministic, and we can create predictable patterns onto the surface. Okay, so I'm sure everyone in this audience is familiar with the basics of wetting and non-wetting surfaces, but I'm going to focus on non-wetting surfaces and superhydrophobic surfaces mainly here. In static conditions, when the static contact angle of water droplet, I'm talking about water mainly in this talk, if the contact angle is equal or larger than 150 degrees, we call the surface hydrophobic, superhydrophobic. But in reality, when you go to dynamic wetting, the situation is more for your surface to be superhydrophobic. In majority of the cases, we need it to be slippery, meaning that with small tilting angle, the water droplet, you expect it to fall off the surface. There's a lot of application and a lot of observations that many of these superhydrophobic surfaces can behave actually in a sticky manner, which means that the water droplet contact angle is quite large, but even when you tilt the surface 180 degrees, the water, and even if you pull on the water, it sticks really well to the surface. And so I run the biomimetic lab. I'm going to say something about biomimetic engineering. And so you see these type of surfaces from slippery to sticky across different natural materials. If you think about, we work a lot with wings of insects, which are typically superhydrophobic but slippery. So if you drop a water droplet on the surface, it never really wets the surface. There's always that nano layer of air that is trapped on the nanostructures of the surface. But you see also lots of insects that have hydrophobic, quite large water contact angles, but very sticky behavior. Similarly, you see a lot of, this was probably more commonly accepted way before the insects, that you have lots of superhydrophobic leaves of plants that are slippery. So if you look at the water droplet on a lotus leaf, it almost feels like, it doesn't have any friction on the surface. But you see lots of plants, actually more than the slippery cases, that hold on to the moisture and the water droplets. And they have the water droplet is it has very large contact angle, but it sticks to the surface. So where does this behavior wetting management comes from? It comes from this waxy layer on top of the surface. If you want something that is slippery, you typically, in the plants, in the larger scale designs, you have this micro scale. On top of it, you have a nanoscale structure. For the cases where you have a sticky behavior, wetting behavior, still superhydrophobic but sticky, you have these larger structures, and the smaller structures are only at the tip of these bumps. We know, at least in terms of plants, that these structures are crystals of waxes. So already looking at these crystals, we know that crystallization is, and that's where the whole idea that we had about crystallization came from. Crystallization is a really good technique for creating large scale, for creating small scale surface pattern over larger scale areas. And in fact, from 1960s, 1970s, plant biologists, they knew that these are crystalline structures. So from the start of the electron microscopy days, they looked at the crystal structures on different leaves of plants, and they tried to extract the wax and recrystallize it. And they got quite similar, depending on the plant, they got quite similar structures. So we know that the chemistry and the physical topography in nature are linked in most cases. And we wanted to pick up similar chemistries, because these are already chemistries that are hydrophobic, but you add the structure to it, so you increase you get superhydrophobicity. But in nature, normally this is done by tuning the chemistry. So every time you want to get a new physical topography, you change the chemistry. And our main objective was, can we actually keep the chemistry constant and do some physical manipulation and change the environmental and this kinetics of phase change and crystallization to be able to change the physical topographies, and then look at how the physical topography controls the wetting behavior. So I said that we are after sustainable sources. It's not really sustainable to extract the waxes directly from plant leaves and recrystallize it. So we started looking at waxes which are already available. Most of the plant-based oils, to be purified, there's an element, there's the wax element that needs to be extracted from it. And if you can make use of it, it's always a gain. The only thing that's not plant-based here is the beeswax that we also use. So I'm going to pick one of these, but we tried this technique for a majority of these waxes in this graph. The only thing you need to look at in this graph is that these waxes, they're typically hydrophobic materials, but the contact angle that you're looking at is the contact angle on a smooth layer of these waxes. And with a smooth surface, you can hardly get to above 110 degrees of water contact angle. And to be able to get to angles such as 150, you really need to add surface roughness to these ones. Okay, so I'm going to use rice bran wax in the next few slides. And we use rice bran wax, which comes from the bran around the rice. And it's a small quantity, so really the rice bran itself constitutes around 8% of the grain of rice in weight, and 2 to 3% of this rice bran is actually wax. But we use loads of white rice, and the rice that we grow looks like this one at the bottom right. The rice that we use is at the top left. So there's lots of materials that goes to waste. And again, rice bran wax, it is starting to find some usage in different applications, but it's going to waste otherwise. These waxes are typically solid at room temperature. So if you want to make a coating, you need to melt it and then create a coating like out of a liquid and then wait for it to solidify. If you melt and solidify, it's going to give you just a few wrinkles. But if you add solvent and solidify or crystallize by solvent evaporation, now you create these beautiful structures onto the surface. So you're looking at exactly same chemistry, but just changing the crystallization path from cooling crystallization to evaporation induced crystallization. And obviously, because you're adding surface roughness, you're increasing the water contact angle on these surfaces.
Sepideh, maybe in a favor of time and to give some also space for participants to ask questions, if you could wrap up in the next couple of minutes.
Yeah, I'm not too far from the end, Chiara.
Thank you.
So just to tell you that these two surfaces, they look quite different, but in reality, the crystal structure at molecular scale, they're identical, okay? Second question is how much really can you change this topography? How can you change? If you can change it, how can you change it? So the first way you can do this is by controlling temperature. And the second way that I'm going to focus on mainly in the next 1-2 slides is the changing the solvent. If you use solvents that evaporate quite fast and create a large gradient of concentration in the film, you create structures that are really nanoscale pores on the top of the surface, and you create these super hydrophobic surfaces. If you use solvents that are low, that have low vapor pressure, and they evaporate slowly, then you create larger structures. So beyond the structures that you get, as I said, these structures, they will have direct influence on the wetting behavior of these coatings. So if you have smaller structures produced by fast evaporating solvents, the surface is super hydrophobic, but it's very slippery. On the other hand, if you use solvents that evaporate slowly, you get super hydrophobic surfaces, but very sticky surfaces. And you can tune these surface structures by mixing different solvents and tune the evaporation rate of the solvent and get all the different types of wetting behavior that you're after. And I showed you the results for the rice bran wax, but these are the results. You get similar trends when you use different types of waxes. So this is still undergoing in development research, and we are still looking at understanding the kinetics of this phase change crystallization and trying to mix it with the fluid mechanics of coating. But to say that it's quite easy at the end, because you start with a isotropic fluid that is low viscosity fluid, so you can use it for coating internal, external, coating fabrics, and all the things that I showed you at the smaller scale for wetting manipulation. You can get slippery and sticky surfaces on a variety of different materials using this kind of crystallization techniques. So this is just an acknowledgement slide. And with that, I'm all done. And I mean, I suppose you are all convinced that surface matters, but just to close, it matters when you think definitely about phase changes of different types of phase changes, evaporation, nucleation. But then I showed you also at least one example where we can use these kind of phase changes to then be able to create surfaces that we can use for manipulation of fluids.
Thank you very much, Sepideh, for this insightful and very interesting presentation that covered 3 different main areas. So it was really, really interesting. I now leave some time for participants to ask questions if they might have anything to ask, either directly unmuting yourself or writing the message questions in the meeting chat. Maybe I can start with the first question while other people warm up. Is more related to the first part of your presentation, the first, let's say, pillar. I remember you showed the effect of the theta angle. I mean, you were talking about local dry out of the thin film in non-asymmetric channels, and it's indeed a very useful and practical problem for many engineering applications. You show that this can be function of different parameters, and I was wondering which parameter accounts for different materials. Is it, of course, the angle, so that is related to surface wettability and contact angle, or is the material of the type of channel you are testing as an impact on that?
So, I mean, we use contact angle as a sort of a macroscopic measurement of nanoscale molecular scales. It really depends. I would imagine, so I work mainly with water. That's why I always use water contact angles. But majority of the industrial applications, they deal with materials which are actually not at all like water. So still you need to characterize some sort of wetting. Surface roughness is quite probably, when you start getting to film thicknesses which are order of micrometer or smaller, you should start looking at the surface roughness relative to the, but still if you have a rough surface that's really wetting for your liquid, is probably beneficial because you will have always a coated surface on the channel. But if you have a surface roughness in a material that's not wetting, then you have the opposite effect.
Yeah, I can see it's a kind of a trade-off or combinations of the two. All right, thank you very much. I can see Marco Graffiedi raised his hand. So I suggest you just briefly introduce yourself, Marco, which university you're from, what do you do, and then ask the question.
Sure. Thank you, Chiara. So I'm Marco. I work in the Professor Bucci's lab here at MIT. Thank you, Sepideh, for the talk. Amazing. I have many questions, but just one, just to like, because there is one thing that I would like to understand. So you talk about recrystallization, and if you use plasma cleaning, then the recrystallization is faster, right? I already saw that plasma cleaning it is used also in boiling heat transfer because we have like the deposition of hydrocarbon on the surface. Is that the reason why the recrystallization is delayed, or do you think it's something else?
Yeah, so it does also remove, so it removes any kind of contamination from the surface. It increases, so again, when you think about crystallization and the phase change, the phase change that I had, the molecules, they have, they're charged. So they will stick to my surface. And the more higher, at least water wetting it is, the better they will stick to the surface. So it's just going to increase the rate of transfer of the molecules to the surface and increases crystallization. But if the crystallization is out of hydrocarbon molecules, you probably want to have more hydrocarbons on the surface. So I think it depends what is the material that's going to aggregate onto the surface.
Oh, okay.
But in general, it just sort of gives you a cleaner surface with a higher surface energy that then they typically increase the phase change.
Okay, thank you. Yeah, yeah. I need to study a little bit more about this. Okay, thank you very much.
Thank you for your question, Marco. I can see people in the chat thanking you for the very nice talk. Any more question? Young Subsong raised his hand, so maybe. Hello.
I think Dr. Garimella was about to say something. I think he can go first.
Oh, sorry, I can't see all the cameras. Of course,
yeah,
sorry.
I didn't raise my hand, but anyway, Sepideh, nice talk, a very nice overview of several different applications. One of the topics had to do with sort of enhancing heat transfer, mass transfer, things like that. But I just wanted some clarification. Are you planning to do heat and mass transfer experiments, or is it primarily sort of interpreting the heat transfer potential based on the fluid mechanics part? Will you be doing heat flux and temperature measurements and so on?
No, so I mainly do adiabatic work, and the numerical work that I was showing was from other groups. So I tend to, instead of solving problems, I tend to create problems. So I just saw this in adiabatic solutions and asked people to see if they see similar trends but no, we don't do any diabatic measurements.
Okay, thanks.
Thank you, Professor Garimella, for your question. And then I go to Young Soup, who was also asking a question, please.
Yeah, thank you for the very nice talk. I'm Young Sup. I'm an assistant professor at University of Florida. So I have a question for your chapter 2, I think, when you have surfactant and its concentration or precipitation. So I think it's slide 31, if I remember correctly. You show that you can detect the kind of precipitation from the shallow, like less volume, like solution first, compared to like large volume solution. And you explained it based on the surface to volume, like ratio, surface area to volume ratio, basically. And I was kind of confused at that point because I was thinking you were measuring the very first precipitation. So I thought very first precipitation should be kind of more closely related to the like just absolute surface area, not the ratio of surface area to volume, right? Because if you have larger surface area, like not the ratio, then you have more kind of potential nucleation sites, basically, right?
Yeah, so there are multiple points there, probably. There is also besides the resolution of the technique, space resolution, there is also the detection, the field of view that you have in the technique. So we always detect things only within the field of view that we have. The other thing is that, yeah, as I mentioned, these are all stochastic processes. So it's going to appear randomly. The more surface you have compared to the volume of the liquid, I would imagine the more surface that you have for the same volume of molecules, you will have more probability that you will have stochastic nucleation on those surfaces. So like in industry, what they do, they introduce extra surfaces into it. You can add particles into the volume, or you can add mixers with adding another surface into the. So I would imagine it's per volume of the material, you want to have more surfaces to start. And again, these are multiple. So if you think about one single experiment, yeah, that would make sense. But for a stochastic process and probability of a statistical probability of molecules having the chance to get to the surface.
What you measured is not the probability, right? You measured is the very first moment of precipitation, the time.
Well, it's the very, I call it the very first moment, but it's the very first moment that I can detect with my experimental technique, and it's hardly ever the first nucleus that is formed, because my resolution is always way larger than the first nucleus.
You're assuming that's primarily because of the detection resolution?
Yeah, I mean, it's so I think the only point that I can make is that out of those experiments is that the technique that you use, either for the cooling or the material that you use, is going to shift either the temperature that you report or the induction time for the crystallization that you report. Then in terms of fundamentals of the nucleation and growth is a bit more difficult, because you need something molecular scale at that particular surface and volume. Yeah.
I see. Yeah, thanks.
Thank you for the question. Maybe there is time for last quick question. Otherwise, I don't see all the cameras.
I think Sanjay Kid is maybe trying to ask a question.
Perfect. Yeah, perfect.
Yeah, if I have the time to ask a question. Hello. First of all, thank you very much for your great talk. I have a really simple question. It's related to your first chapter about confined bubbles in either axisymmetry or non-axisymmetry geometry. I just wonder if you have any thoughts, especially in a 3D rectangular channel. And if you suppose if you're flowing your flow in a horizontal way, then there's a chance if your channel is big enough, there could be a slight stratification where your vapor in your flow could be floating up top where your liquid is flowing down. So there could be a non-axisymmetry up and down wise. Can you tell me if there could be a possibility, like theoretically or even numerically, you can like come up with equations or models that you can calculate or predict the thickness of a liquid film?
Well, it was one of the scenarios that we have studied, at least in the axisymmetric geometry, at the regimes where the bond number is quite small and you wouldn't expect any significant effect. What we see is that exactly what you said. The film is thinner at the top, thicker at the bottom. But not only that, because it also leaks from the top to the bottom, the film. So you get inclination of the bubble and the different films. So I can send you the papers that we have. There is numerical paper and there is a experimental paper on the topic. And there's some theoretical work. I mean, the work that we did was theoretical and experimental. And there's also numerical work.
Okay, yeah, that'd be really wonderful. Since I work with Professor Morower in Purdue University, and specifically these days I'm interested in how to predict the CHF, and I'm dealing with horizontal flow, and predicting the liquid thickness is a critical factor to my model. So yeah, I really appreciate it. I'll send you an email right away. Thanks.
Okay, thank you.
Thank you for your question. So I think we can close the meeting now. I wish to express again my gratitude to Sepideh for her amazing talk. I've been a follower since the past years and an admirer, of course, of your work and outstanding results. Thank you again for the talk, and thank you to all the participants and to the questions that create a very nice scientific discussion.